Okay, so what we're going to look at here are how to construct confidence intervals for P. Okay, and what P represents is the population percentage or proportion. Okay, you may have seen a P before when we did the binomial theorem. Okay, P was the probability of success. Okay, that's going to come into play again here. Okay, we're going to say P is the population proportion. Okay, and the good news is you've actually seen a confidence interval before, but probably didn't recognize it. Okay, so if you go back to before the last election in 2012, suppose a news program reports that in a Pennsylvania poll before the 2012 presidential election, Barack Obama received 54% of the vote. You should also notice the poll gives a margin of error. In this case, say the margin of error is 5%. Okay, so much of the time on the screen next to the polling numbers, they'll say plus or minus 5%. Okay, that's the margin of error. So how do you interpret those polling numbers? Well, I think that's something most people can figure out, is that if the margin of error is 5% and it said Obama received 54%, okay, what that's saying is that we expect Obama to receive between 49 and 59% of the actual population vote of Pennsylvania. Now, what we don't need, the whole point of this, to understand this entire concept of a confidence interval, is that we want to be able to make a prediction for what's going to happen in the actual election. Now I do recognize that 2012 has already happened, okay, but the point is, pretend this was before 2012, and the whole idea is you take a poll, ask people who they're going to vote for, and they're going to give you an answer. Okay, in this case, 54% of them said Obama. The only reason there's a margin of error is because we didn't ask every single person who was going to vote in the Pennsylvania election. Now, I don't know what the population of Pennsylvania is, or the number of voters in Pennsylvania, but let's just suppose it's 2 million. Okay, it's probably more than that, but let's just say 2 million people in Pennsylvania voted. Okay, you didn't ask they didn't ask all 2 million people in Pennsylvania. Okay, so they may have asked 100 people, 1,000 people, 10,000 people. 54% said they'd vote for Obama. Okay, so if they asked 100 people, 54% would be 54 out of 100. If they asked 1,000 people, then 540 would have said they're going to vote for Obama. Okay, so again, the whole idea here is what a confidence interval does. It allows you to make a prediction or an estimate for the actual population. Okay, and that's extremely important. All right, so as we move along here, just a lot of reading here. Okay, P, just like with the binomial, P is the probability of success, and P is the population proportion. So that's the actual percent that voted for Obama. That number we do not know until the actual election happened. P, with that little mark over it, we say that, or pronounce that as P hat. Okay, we call that P hat. Not fat. P hat. Okay, that's X over N, which we call the point estimate for P. Okay, so that is our estimate where we expect the population percentage to be. Okay, so P hat is the sample proportion of X successes and N trials. So in this case, if we asked 100 people who they're going to vote for, X would have been 54 and N would have been 100. So 54 out of 100. If we had 1,000 people we asked, so 1,000 trials, X would have been 540 in this case to get 54%. Okay, and then we have Q hat, and all that is a complement of P hat. So 1 minus P hat, which represents the sample proportion of failures in N trials. In this example, it's the sample percent that did not vote for, or that said they would not vote for Obama. Okay, it's the sample percent that didn't vote for Obama. So what do we know in our example? Well, P, the population percentage or proportion, we don't know. Now again, we're pretending we're before the election. So we don't know what P is. We don't know how many people they asked in our survey. Okay, they didn't tell us they polled 1,000 people or 100 people or 500 people. They didn't tell us anything like that. So we don't know either of those. Okay, P hat we know that 54% said they're going to vote for Obama. So Q hat would be 1 minus P hat, which is 0.46. Again, we don't know N and we don't know X. We don't know the number of people that said they were going to vote for Obama. We just know that percentage that said they'd vote for him was 0.54. Not vote for him, 0.46. Okay, so we only know two things in our example. Okay, and at the bottom of the page, it's essential to understand that we're using a sample to estimate the true value of a population. Since we use P hat to estimate P, we must be aware of a margin of error. If we chose a different sample, we may get a different value for P hat, and therefore a different interval estimate. Okay, so that's essential that we understand that. That just suppose they asked 100 people. If they ask another 100 people, they may get a totally different result. Okay, if you ask 100 people in a certain neighborhood, maybe 70% said they'd vote for Obama. Maybe 20% said they'd vote for Obama. Okay, so it matters who you asked in the sample. Okay, so it's important to recognize if you took a different sample, you may get a different estimate. Okay, so in our example, we made an interval estimate around P hat where we hope our interval will contain P. So 54% plus or minus 5%, which was the estimate, plus or minus the margin of error. Okay, so E is the error. So that gave us the interval of 49 to 59%. Okay, so how do we actually construct a confidence interval? Well, first thing, we need to make sure two conditions are satisfied. We need N times P hat and N times Q hat to be greater than or equal to 5. Now think about what that saying is. P hat and Q hat are both numbers between 0 and 1. Okay, like 0.6 and 0.4 or 0.5 and 0.5. N is your sample size. So we're basically saying that when we multiply your sample size times P hat or times Q hat, we want to get a large enough number, okay, larger than 5, so we can say the binomial is approximately normally distributed. And the reason we're calling this binomial is because when we asked if they're going to vote for Obama, it was either they're going to vote for Obama or not for Obama. Okay, so there were two choices there. Okay, so we recognize that it is a binomial to start with. Okay, and if we have a large enough sample, we can say we have an approximately normal distribution. Okay, so that's not something I'm going to overly test you on, but it is essential to understand that we are taking a binomial situation and assuming that it's approximately normally distributed. The significance of that is when you have a normal distribution, what can we do with a normal distribution? Use z-scores to find probabilities. Okay, the endpoints of that interval are P hat plus or minus the margin of error. The margin of error, now we're not going to focus really on where this comes from, but recognize what the margin of error is. Z of C, okay, which is a z-score, which we'll explain in a minute. Okay, it's a z-score times the square root of P hat Q hat over N. Well, in reading that last question, we know when we go back and do P hat plus or minus E, P hat we're going to know. In our question, it was 54% or 0.54, plus or minus the margin of error. Z of C, that's a z-score that we're going to find. P hat Q hat, we're going to know from the problem. In ours, it was 0.54 and 0.46. And then N, well, in our problem, we didn't know that. But to construct a confidence interval, you have to know what the sample size is. Okay, and the way we're going to interpret our confidence interval is that we are C% confident that our confidence interval contains the true value of P. And as we do an example, we'll explain exactly what that means. The most common values of C are 90, 95, and 99%. So think about when you make a prediction about something or estimate something, you want to be confident in your answer or in your estimate. Well, you don't want to be 5% confident. Okay, like if I ask you to pick the Super Bowl winner or pick a winner of an event, you don't want to be 5% confident. You want to be like 90% confident or 95% confident. Okay, so those are common values for C. Okay, so what does that mean? if we want to find Z90, what that's basically saying is, because our estimate is centered around p hat, we're adding, subtracting the same margin of error from p hat. So p hat's like in the center of your estimate. We're basically saying that Z90 means that we want to look at the middle 90% of the distribution. So the middle 90% straddles around the z-score of 0, so we have a negative z and a positive z. And the way you find that, this goes back to previous chapters, if you have 90% in the middle, that means there's 10% to split between the two sides, or the two tails I should say, which is 0.05. So if you do the inverse norm, 0.05, and then the mean 0, standard deviation 1, that tells us we're looking at the standard normal distribution, you get negative 1.645. Okay, now the idea here is that z of c, if you have a confidence level of 90%, that z of c value is going to be not 90, but 1.645. Okay, now the plus or minus, all that's saying is the middle 90% is between negative 1.645 and positive 1.645. Okay, that's all that means. Don't focus on the positive negative piece of it, because that's already taken care of with the plus or minus here. Okay, so basically you're looking at 1.645 for Z90. For Z95, you're looking at the middle 95%. So when you look at the middle 95%, okay, I'm not going to explain all the way through this, but you have 5% left over to split between two tails. So 0.025, you can find that z-score of 1.96. And then Z99, the middle 99%, you have 0.005 left over on each tail, and that's a z-score. Now it's interesting on this one, if you use the inverse norm, you get negative 2.58 when you round it. The table gives you plus or minus 2.575. Okay, so just be aware that there might be two different values there that you see used. Okay, so that's how you find the z sub c value for one of these questions. Okay, and the good news is those numbers are never going to change. If I tell you to construct a 90% confidence interval, or an interval with a 90% level of confidence, you're always going to use 1.645 for that z sub c value. Okay, so they're going to use those numbers all the time. Okay, so an example of a confidence interval. Okay, I think you're going to find this is really pretty easy. Okay, in a recent survey of 500 people, 150 people said that they believe George W. Bush was a good president. Construct a 90% confidence interval for the proportion of people who say Bush was a good president. Now I could also word this as construct a confidence interval for P and with a 90% level of confidence. Okay, so be aware there's different ways that could be worded. Okay, but basically what that's saying is we're looking at a C value of 90%, which means we're right here with a z-score of 1.645. Okay, so as we go through the question, the first thing we recognize is that we're constructing a confidence interval for the proportion of people. Okay, so that's a confidence interval for P, which means we're using this up here, P hat plus or minus E, where E is Z sub C times the square root of P hat Q hat over N. Okay, so we recognize that this is the formula we're using. Now, even more good news, I will give you a formula sheet with that formula on it. Okay, if you choose to do this by hand, okay, you'll have a formula sheet with that on it. Okay, so now it's basically just plug and chug numbers. Well, P hat is a sample percentage that said that Bush was a good president. Well, that is 150 over 500, which is 0.30. Okay, so that's what P hat will be. Q hat is the complement of that, or 0.7. N is 500 because we took 500 people in the survey. Okay, there are 500 total trials or people. And then your Z90 is 1.645 for reasons above right here. So it's plug and chug. into that formula. Okay, and if we do this by hand, if I tell you I want to see the work, okay, what I need to see is the substitution, so I need to see this. And then what I want to see is E, the margin of error. So what is 0.1645 times that square root? Now I'm going to show you one time how to enter that in your calculator just to make sure you're on the same page as I am. Okay, and doing the correct thing. Okay, let me this up here. So if we do 1.645 times the square root of 0.3 times 0.7 divided by 500. Okay, notice you can enter all of it once. Okay, it shouldn't be too hard to get that into your calculator. And that's 0.0337. So the margin of error is about 3.37%. So that's what you're going to add and subtract from 0.30, our point estimate for P. Okay, so now to write our answers, there's two ways we're going to write our answer. What we're basically saying is if you add and subtract that margin of error from 0.30, we're saying that P, we're 90% confident that that interval will contain the value of P. Okay, so we're 90% confident that P, the true population percentage. So if you were to ask the entire population whether they thought Bush did a good job as president, we're 90% confident, based on this sample, that between almost 26.6% and 33.4% would say he did a good job as president. Okay, so that's one way to write the answer. Okay, the other way to write the answer is to write it in what we call interval notation, which you may not be familiar with, but all that is I mean, it looks like x, y almost, okay, but that is not a point x comma y. That is interval notation for the lowest comma highest. Okay, so that's another way to write your answer. Now I put them both on there not to be confusing, but because you may see that written either way. Okay, if we go to the next example, okay, so you can read that. We're going to construct a 90% confidence interval for the proportion of students. So again, we're looking at a confidence interval for a proportion, P. So that means we're using this formula. Okay, so when you read a question, you need to recognize what are they asking me to do. Okay, we're using this formula. So when you go through the question, they say 82 students work full-time. They ask 200 students. So P hat is 82 over 200. Which makes Q hat 1 minus P hat. So we have 0.41 for P hat, 0.59 for Q hat. N is 200 because that's how many students they asked. And then Z90, again, is 1.645. So again, plug and chug into the formula. And if you need to do this, you can pause the video, but I'm going to move on for the sake of time. And then the margin of error there is 0.0572, so about 5.7%. Okay, add and subtract that from P hat, and we are 90% confident that the true population percentage of students who work full-time is between almost 35 and 47%. Okay, now if we want to use a calculator, I'll show you quickly on the calculator. Okay, we go to stat, and then over to test, and then we're doing a proportion a confidence interval for a proportion. Okay, so as we scroll through this, now there's a lot of options, so you have to really pay attention. Okay, we're doing a one proportion Z interval. Okay, one prop, that means one proportion. Z is we have Z scores. Okay, we're using Z of C here. And then INT means interval. So in our example, X is the number of people that we were success that said they work full time. That's 82 out of N, which was 200. And the confidence level was 90%, so 0.90. And then calculate, and notice same answer as this. Now every once in a while you may be just a tad different, or they may use more decimal places here sometimes depending on the numbers, but it should be very close. Okay, so there are the calculator steps that you'd have to show. Okay, you go to stat, test, one proportion Z int, and then enter the values in. Okay, now for the sake of time, the next ones I ask you is a 95% confidence interval. So given the same information, except instead of 90%, we're going to be 95% confident. Okay, so if you want to pause the video, you can go ahead and work on that. Okay, I'm going to show you the answer. Okay, and then the answer to the 99% confidence interval. Okay, if you fill in the values there. Okay, so again, once you get the idea down, it's really pretty straightforward to plug and chug these numbers in. Okay, so in part D, as you examine your results from A to C, what can you say about the confidence interval as the level of confidence increases? So as we go from 90 to 95 to 99% confident. So as we gain confidence in our estimate, notice what happens to our interval. We go from, say, 35 to 47%, from 34 to 48, from 32 to 50. Okay, so what's happening with our interval? As we become more confident, the interval gets wider. Okay, so what happens? The interval gets wider. Okay, or there's a wider range from the minimum to the maximum. Okay, and basically all that's saying is, and why the reason is when you look at each of these initial steps up here, the only number changing, we go from 1.645 to 1.96 to 2.575. So the more confident you get, the larger that z-score gets, which means the margin of error gets larger. Basically saying, to become more confident, you have to allow more values to be within your estimate, or to be within your interval. Not your estimate, within your interval. Okay, so if you want to be more confident about something, you have to allow more values in. Okay, it's like saying if I wanted to predict the score of the final score that a winning team scores in a football game, if I were to say the winning team is if I'm going to predict or estimate that the winning team is going to score between 30 and 31 points, I probably shouldn't be very confident in that. I might be like 10% confident in that. But if I said the winning team is going to score between 10 and 30 points, I would be more confident in that prediction. So I basically, to become more confident, I have to allow more values into the interval. Okay, so moving along to the next one. Okay, now what we're going to do is we're going to look at we're going to increase the sample size to 400, and suppose 164 students said they work full-time, and we're going to construct a 99% confidence interval for the population, for the proportion of students who work full-time. So now when you do p hat will now be 164 over 400. But we notice that's still 0.41. So it's the same percentage as before. The only thing that changed is we're taking a larger sample size now, and we had more 6 sample size also. So now how does that affect the formula? Well, when you plug your numbers in, that 0.41 is still p hat. 2.575 is our z-score for the 99% confidence interval. And then 0.41 times 0.59 over 400, because our sample size is now 400. And notice what we get when you do all those calculations there. Okay, what happens? We get 0.3467 to 0.4733. Okay, and you can do it on the calculator. I put the calculator values there. Okay, so what happens? If we look at the results from C and E, what happens to our confidence interval as n increases? So as n gets larger, what happens? Well, in part C, our confidence interval was from 0.3204 to 0.4996. Well, here what happens? 0.3467 to 0.4733. So we're 99% confident in each of them, okay, in each of these two. But the n value here is larger now. And what did that do to our margin of error? Our margin of error went from almost 9%, or 0.0896, down to almost 6%, 0.0633. So what that did to our interval, it made it more narrow. Okay. So our confidence interval becomes more narrow. The reason we get a smaller answer there is when n increases, what you're essentially doing is dividing by a larger number, meaning your answer gets smaller. Okay, last thing we look at here is suppose you're asked to find a minimum sample size that you need. Okay, so suppose we want to think about, well, if you want to be within 3% of the actual population percentage of something, how many people do you have to sample? Or how many have to be in your sample size? Okay, so to answer that, we take our margin of error, and then basically you want to solve for n. Okay, so we're saying we want to find what does n have to be. So to do that, I have the steps written out here, but to follow through, divide each side by z of c. Okay, so that's this equation. And then, to get rid of a square root, you square each side. So that squared would get rid of it on the right-hand side, and you square the left-hand side. Well, that would give you e squared over z sub c squared, and then p hat q hat over n on the right-hand side. And then, how do you get n equals? Well, basically cross-multiply. If you multiply each side here by n, they'd cancel here. Multiply by n there. And then, to get rid of the z of c squared, you multiply that over here, so that's on the top over here, and then divide by e squared, so that's in the denominator. Okay, so that's how you find the value for n, which will be the minimum sample size you need to estimate p. Now, if we don't know p hat or q hat, you have to use 0.5 for both. Now, I'm not going to go through the entire explanation, but the basic idea is you want to, if you have 0.5 for p hat and q hat, when you multiply those, that'd be 0.25. So 0.5 times 0.5 is 0.25. If you use different values for p hat and q hat, let's just say if p hat was 0.3, q hat would have to be 0.7, and that results in 0.21. Now the basic idea is if you take any p hat and q hat and multiply them, 0.25 will be the largest it can ever be. So that'll result in a maximum error. Basically saying we're going to err on the side of caution. Okay, so the few examples of these in number 6 is just plug and chug. How many shoppers must be surveyed? So how many shoppers is your survey, is your sample size. n, so we're trying to find n. Construct a 95% confidence interval for the proportion of shoppers who spend more than an hour in a shopping mall. We want a margin of error of 3 percentage points. Okay, so the 1.96, that's your z of c value. Okay, so that's z sub c up here, 1.96 squared, and then 0.5 times 0.5. They didn't tell us, they took a sample with a p hat of 0.2 and q hat of 0.8, so we're using 0.5. We're applying this rule right here. And then the margin of error is 3 percentage points, so 0.03 squared. Okay, so that's just using this formula here. Then it just plug and chug, you get 1067.11. We're always going to round up to the next integer. Okay, because you have to survey 1067.11 full people to get the result we want. Well, we can't survey 0.11 people, so you go to the next value up every single time, the next integer up. Okay, if you chose to use the original formula, plug the numbers in. Okay, so if you chose to use this form, okay, which is perfectly fine, because I'm not going to give you this on your test. I'm not going to give you this formula, but you will have this as part of your confidence interval formula. So if you want to plug and chug into that, okay, I go through the steps here. So if you want to follow through that, you can. I'm not going to go through and explain each step though. Okay, I'm going to move on to the last example because we're getting long on time here. 10 minutes ago, we're getting long on time. Okay, the very last example, similar to the last one. 110 out of 165 shoppers say they spend more than an hour shopping. How many shoppers must be surveyed to construct a 95% confidence interval? And we want a margin of error to be 4%. So now they did take a sample, and these were the results. 110 out of 165 say they spend more than an hour shopping. So here, p hat is 110 over 165. That's 0.66 repeating. Q hat will be 55 over 165, or 0.33 repeating. Now the reason I'm not going to use those decimals, because we would have to round. We would have to round our answer. So we're going to put in the actual fraction. Okay, so again, z of c is 1.96 because we still have a 95% confidence interval, so that 1.96 is still the same. P hat times q hat divided by the margin of error squared. So do all that arithmetic in your calculator, and you get 533.56. Well, we're going to round that to 534. So we would need to survey 534 people in order to get those, be 95% confident within 4% margin of error. Okay, so that is constructing confidence intervals for P, the proportion or percentage.